Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 3 Part B. The problem states a column has two equilibrium trays set between the total condenser and the feed stage and two equilibrium stages between the feed and the reboiler. The feed flows in a F equals 1 mole per second with Z equals 0.5 mole fraction of the more volatile component. The relative volatility is assumed constant at 2. Liquid flows via overhead at a rate of 12 times holdup minus holdup naught to the 1.5 power, where holdup naught is 1.2 moles for all stages. The trays are filled throughout initially with the feed liquid at a holdup to yield liquid flows consistent with a distillate flow rate of 0.6 moles per second at a reflux ratio of 1. The condenser and the reboiler are also filled with the feed liquid at initial holdups equal to 10 times the holdup in the rectifying and stripping section, respectively. A proportional level controller with Kc equals 1.5 is used to adjust the bottoms flow with the reboiler holdup as a control objective, i.e. bottoms flow equals nominal B plus 1.5 times reboiler holdup minus 12 moles. Nominal B equals F minus D equals 1 minus 0.6 moles per second. Simulate the time response of the compositions and holdups in the column over 500 seconds. So we can switch over to Google Colab, where our first step in simulating this situation is going to be importing our libraries. So import NumPy as NP from SciPy integrate import solve IDP, and from plotly dot subplots import make underscore subplots. Next, we want to set up our distillation column. So I have the problem statement pulled up here on my iPad to make it a little bit easier on us. And it says that there are two equilibrium stages between the total condenser and the feed stage. So that gives us, if we count the condenser and the reboiler as stages, one for the condenser, plus the two for the equilibrium stages at the top, another for the feed stage, two for the equilibrium tray stages on the bottom, and then another for the reboiler, giving us 7 total stages. It then says that our feed flow is 1 mole per second, and then it has the mole fraction of 0.5. The relative volatility, which we'll call alpha, is equal to 2. And then we have our Francis Weir constant, which is going to be equal to 12. Our initial holdup is 1.2. That's moles. We have a distillate flow rate of 0.6 moles per second and a reflux ratio of 1. And then we have a Kc for our controller at 1.5. It tells us that our bottom flow is F minus D. Now that we have all that set up, we can start looking at each individual sections of the column. So that's our top and our bottom. And we're going to start by looking at the liquid flow in these sections. So for the liquid in the top section, we're going to have R times D, since we know our reflux ratio is L over D. And then the number of moles in this section is going to follow the Francis Weir equation, and so that gives us LT divided by FW. constant to the third power plus m naught. And if we look at the liquid flow of the bottom, we are going to have the liquid from the top section plus the liquid from the feed. That will be Q times F. And we need to establish a Q. Q is the fraction of liquid in the feed, so we're going to make that 0.9. And then the moles follows the same thing for the bottom that it did the top. We're going to take from our Francis Weir. Power plus m naught. Now that we have that set, we can look at our vapor flows. So for the top, your vapor is the liquid flow in the top plus the distillate that's being drawn out. And then the vapor for the bottom is the vapor in the top minus the vapor that came in from the feed. That's 1 minus Q times F. And finally, we want to set up our composition on each tray. And that's just going to be n full. And each tray is going to start with Z as our mole fraction. And then the number of moles on each tray. If we start by looking at the condenser, we said that we wanted to have 10 times the amount of moles that one of the trays does, so 10 times empty. Then we have our two top equilibrium trays. And then if we include the feed tray as one of the bottom trays, we have B times 3. And finally, the reboiler is going to have 10 times the hold up at one of the bottom trays. Now we can hit Shift Enter and move on to making our function. Actually need to do NP there first. Okay, now we can define our function. So we can say define right hand side. It's going to be our independent variable of time, and then a vector. And our vectors are going to be our composition and our number of moles. And the functions that we're going to be evaluating are those mass balances, the differential equations that came from those in part A. But to do that, first we need to establish a couple things. The first thing that we want to do is say that x and m are our vectors, but we want to split them. And we can look at them separately. And we want to look at these in a set of arrays. So we want to set them so they're all 0 first, and then we'll fill them in. So 0's like m. And then we'll have dx. 0's x. And then along with these differential equations, if you remember, they had the flows going in and out of the tray, so we need to set up an array for that as well. So we're going to have our L M V equals NP dot 0's like M. Okay, now that we have that set up, we can start filling in some values for those arrays. So we can start with our condenser, where we're just going to have R times D. And then we have our vapor in the top, which we kind of already established, but we're going to put it here as well. So we're going to have R times D plus D. And then for our bottoms, bottom is equal to BT minus Q times F. Now, if we wanted to make an array of our vapor flows, we would have, starting with the condenser, we would have 0 since we have a perfectly controlled condenser. Then we would have our vapor flow in the top, and we're going to have 3 of those stages. So if we have our top 2 equilibrium plus our feed tray. Then we have our bottom trays, and we're going to multiply that by 3 since those are our bottom 2 trays and our reboiler. Perfect. And then we are going to look at our reboiler a little bit closer. We said we were going to have a proportional controller for that, so we have controlled B is going to be our B plus Kc times number of moles at that tray minus 10 times m naught. Because that's going to control it to be at the number of, or 10 times the initial number of moles that we had. And then we can make this L-1, that's our reboiler, and we're going to say controlled B if controlled B is greater than 0, else 0. Great. Now that we have all that set up, we can go ahead and start evaluating dm. So dm for our middle trays. Oh, I know what we forgot to do. We need to set our liquid flow rates in the middle for our middle trays. And those are just going to follow the Francis-Weir equation. So that's our m 1 to negative 1 minus m naught to the 1.5 power. Okay. Now we're going to move on to dm. dm, and for our middle trays, what we had was just that normal mass balance. So we had the vapor from the tray below going in, so that was 2 till n, plus the liquid coming in from the tray above. So that gives us the last, minus the vapor flow rate of the tray you're on, minus the liquid flow rate leaving the tray. Now, our third tray is our feed tray. What you have to do here is add in the feed to that tray. And then our condenser and reboiler are also a little bit special. So for our condenser, we're going to have the flow of the very top tray, the vapor flow, minus the distillate flow minus the reflux times 1. And then for our reboiler, you have the flow coming in, the liquid flow coming in from the tray above, the liquid flow leaving the reboiler, and the vapor flow leaving the reboiler. Now, if you remember from Part A, the difference between our overall mass balance and the mass balance of the most volatile component was multiplying by the mole fraction. And that's how we got dm x. So that's what we're going to do here. And first I'm going to add in all my x's before I forget. And then we just have to go through and multiply each piece by the mole fraction. But we do have x and y's for that, and right now we have our x established but not our y value. So to do that, since we're at constant relative volatilities, we can use the equation x times alpha divided by x minus 1 plus x times alpha. Good. Now we just go in and add these here. X 2 that y from 1 x from 1 to 1. For the feed, it's going to be z, as we established at the beginning. This is going to be y d. For this, I'm going to put this in parentheses and multiply by x 0, since that's our condenser. Just gotta switch this sign. There we go. And this is x 2 x 1 and y 1. Now we can solve for dx, which is what we actually want. So dx is equal to dm minus x times dmx minus xm, which is x times dm divided by m. Then we're going to return p dot r dx dm. And hopefully that works. Looking over this code, I did spot one small mistake before we move on to our solve IVP and plotting. This here should be 1 minus x, not x minus 1. I'll make sure we get that right. But now that we have that, we can go use our solve IVP function. As usual, we do need to establish a Tn. In order to do this, we said we wanted to do this for 500 seconds. Now we can say res equals solve underscore IVP. Our function is our right-hand side. Our time is 0 to t end. Our initial guesses, we're going to concatenate, and it was xi and mi. Method is redo, and then thence underscore output is true. Okay. Now to plot, we can say that tplot is equal to np dot linspace. That's going to go 0 to tn 50, and then x's m's is equal to np dot split res sol tplot, splitting it into 2, and we want to cut it on axis 0. Now for our plot, as usual, is make underscore subplots, and we want one row but two columns, so we can have two plots right next to each other. Now we can loop this. We could say for I x m in enumerate zip x m's. Now we can make our scatter plots. Add underscore scatter. X is t plot, y is x. Mode, we're going to want lines. Its first one is going to go in row 1, column 1. The name is x, whatever iteration we're on. And for M, we can just take this piece right there, copy paste, change this to M, change it to column 2, and this X to M, and then just update the layout, make it look a little prettier with perfect. And here we have our two plots. On the left, we have the tray composition, and on the right, the number of moles in each tray. On the left, we can see that the trays go to steady state, which is what we would expect. All the compositions start at our feed composition here at 0.5, and we can see how they evolve over time into these different steady state compositions. On the right side here, we see that the majority of the trays, those middle trays, stayed flat here, and this is because we had overflowed the tower, so it was already at a steady state when we started simulating this, so this is exactly what we would expect. Now these two up here are higher because we said that we wanted our hold up on the condenser and the reboiler to be 10 times what we're seeing in the tray. The condenser is the red line here that stays constant the whole time, and this is because we have a perfect controller on the condenser, whereas on the reboiler we do see a bit of a change there, and that's because it's a proportional controller, so you are going to see some changes when you use that kind of controller.